So light is created by things, stuff, right? The sun creates light. The lights create light. We create light. We just create light that we can't see. We create infrared light. Okay, so everything creates light. So how is it created? So the basics of how it's created is particles vibrate. And release energy. Okay, some of this has to do with radioactive decay, which we'll talk about a little later, probably the next unit that we do. Some of it has to do with radioactive decay. Some of it is just objects vibrate. When they vibrate, they release energy. Like they shake and they move and they release energy. It's just how it works. Some of that is different types of radiation, but they release light. Okay, so how fast they vibrate determines what type of light is produced. For example, the rate at which your particles in your body vibrate release infrared light. When you get hot, they vibrate more, release higher frequencies of infrared light. When they get cold, they vibrate less and release lower frequencies of infrared light. Okay? Trees don't vibrate very much, so they release very, very low amounts of infrared light, even down into like microwave range almost. So depending on how much they vibrate, release different things. For example, the sun vibrates very fast and releases mostly yellowish light and orange. Some stars vibrate a little less and they release more red. Some stars vibrate a lot more and they release blue or white. We'll talk about this when we get into the astronomy unit here pretty soon. So depending on how things vibrate determines on what type of light they produce. Okay, so let's talk about excitation. All right, so here is my little atom. And my little atom has a little electron. Okay, my little atom is called Philadelphia. Okay, this is the Philadelphia atom. Okay, and here's my little electron. And something happened that excited this little electron in Philadelphia. Okay, a green bolt came and his team won the Super Bowl. Okay, a little green light came and hit this electron in Philadelphia, and he won the Super Bowl. Okay? So what happens? He gets excited. He gets super excited, okay? When you win the Super Bowl in Philadelphia, you get excited, okay? So here he is. And the thing is, if you win the Super Bowl, what do you have to do? You got to burn the city down, right? This is what you do if you're in Philadelphia and you win something. You burn the city down. You flip cars, you climb up poles and fall off, you set police departments on fire, lots of good stuff. All these things. So, but you don't want to do that where you live, right? So if you're in this part of Philadelphia, you don't want to set that part of Philadelphia on fire. So what are you going to do? You're going to go somewhere else. You're going to go to a different part of Philadelphia where you don't live, and you're going to set that part on fire. Okay? In other words, you're going to get excited, okay? And then you can't stay excited forever. Okay? Can't stay excited forever. There's only so many police cars you can set on fire. There's only so many businesses you can break into and steal things from. You can only do so much of that before you're not excited anymore. Okay? So then what happens is those people who were all super excited go back to where they were, and they go back to bed. And their excitement kind of goes out the way it came. Okay, I use my ridiculous example to show you this. You have an atom, and it gets some energy, in this case, let's say from green light. So the atom absorbs the light. Well, that atom that electron gains energy. So it can't stay where it is right now. For those of you who remember energy levels in chemistry, can't stay where it is. So it goes to a different energy level. So it gets excited. And it changes energy levels. Okay? But it can't do that forever. So it does what's called de-exciting. So de-excites, which basically just means loses energy. Okay? And so it releases that light. He's sad. He's sad because he got de-excited. Now he's got to wait a whole another year at least to set Philadelphia on fire. Just had to do it for fun.
Their basketball team could win.
Oh!
Or the Phillies.
Not this year. Not this year they can't. Oh, the Phillies could. Yeah, the Phillies could. They could definitely set it on fire for the Phillies. So, what I want you to see is this is what happens. Something produces light. It gets absorbed by this atom. That atom gains energy. Now it has more energy than it would have. It loses that energy and it releases light when it does so. Now, in this case, I gained this much energy and I released the exact same amount of energy. But not all objects do that all the time. For example, you guys know from chemistry, for those of you who took it, there are multiple energy levels. There's not just one. So it's not like they just go from level 1 to level 2 to level 1 to level 2 to level 1 to level 2. They could go from level 1 to level 4 to level 3 to level 4 to level 2 to level 3 to level 1. Okay? They could just have a good old time jumping around. Okay? So what that means is that for each of those energy jumps, you would have a very specific energy level. Okay? So let's look at this. Okay? I'm going to give you a thing. Make sure it's working. Okay? Let me give you a thing. Okay. What you're going to do is when I turn the light box on, you're going to look through the little triangle. You're going to look through, there's a square on the end, on the narrow end. You're going to look through that at the bright light. Yes, I know usually you're told don't look at the bright lights, but this time it's fine. Probably. Okay, and I'll kind of give you some hints on it, and then I'll switch out. Some of these work better than others. So if you're having trouble with yours, I'll switch you out and give you a different one. You are making some progress. I'm impressed. Okay, so here is this guy. I'm going to turn off this light. All right, and what you're doing is, if you look at your little triangle guy, so what you're doing is you want to take the straight side. So there's a straight side, and then there's like an angled side. You want to take the straight side. You want to point the straight side straight to the light. You want to look through the narrow slot at the light, but you want to use your peripheral vision to pay attention to the numbers. So the numbers I usually hold on my left, and I hold it up to either my left or right eye. Shouldn't matter. Let me see how well this is working. This first one isn't always the best one. If it's not, we'll go on to the next one. Yeah, see, this one hasn't been doing that well lately. All right, let's do one that I know works. I would like to do this one because it would be a good starting point, but it doesn't work. But, well, I think it's just way too off to the side. Yeah, it's there. But if you don't know what you're looking for, you're not going to see it. Okay. Let's do one that I know you'll be able to see. There we go. Okay. Let's pick one I know is going to work. Okay. Go ahead and look through your tube. Alright. What you should see is when you look down the light tube again, you gotta kind of play around with it. You want to look so that your eye is pointing at the light tube, but you want to use your peripheral vision to look at the numbers off to your left. Okay, and do you see 3 bands of light? You should see 3 color bands. Yes, no, maybe? Thumbs up, yes, we're getting things. Okay, good. Okay, your excitement level was overwhelming. I couldn't tell. Anyway, so what you should be seeing is you should be seeing 3 distinct color bands. So those bands are what are called emission spectra. So we talked about the light that was absorbed. So what's happening right now is electricity is going into that, which that, by the way, is mercury. Electricity is going into the mercury and it's exciting it. So it's causing those electrons to jump up energy levels. But they can't stay there forever, so they jump back down. When they jump back down, they emit color. And if you look, that's what it looks like. But if you hold this up, what it does is it separates out those colors into the individual colors that they are. Okay? And so what you can see is that there's 3 particular energy levels for mercury. There is kind of a yellowish, orangish one, a yellow-green one, and then kind of like a violet-blue indigo color. So those are the 3 energy levels, and it'll jump between those different energy levels when it gets excited. Okay? And those are the 3 energy levels that it will release. Okay? So, I'm going to show you a diagram of that in a second, but I want to show you some different examples of these 2. So, that was that one. Let's show you another element. So that one worked well. Let's do neon. I know this one also works well. This one's going to have a lot more, by the way. So this one's going to be a lot easier to see. But I wanted to show you one with only a few so that you could see one that had a lot. This one's got like a bunch of reds, yellows, greens, oranges. And again, sometimes you got to kind of play with where your eye is. Like, your eye needs to be able to see that, but you need to look in the corner of your vision to see the lines. Anyone having trouble still, or need me to help show them, or need to try a different one? Okay. Let's do. I really like to try to get some of these complex. Okay. I do want to show you one more thing too, though. So go ahead and take what you're just looking at and look at the ceiling light. Do you still see it? You see how it looks pretty similar to what you were just looking at? That's because the ceiling lights had mercury in them. So because we can look at what mercury creates and produces, when we look at the ceiling light, we can say, hey, we see a lot of that stuff. It must have mercury in it. We'll get to that when we get to stars. That's actually how we figure out what stars are made of. We go around staring at stars with these better versions of these, and we see what they're made of. So anyway, so that kind of gives you that one. Let me bring the basket around and you can put yours in here. then I'll go back to the notes and show you what to write down. But I wanted to show you so you can actually see what these things look like. Did you see what she did to this one?
Dude, no. I walk in here and there's this tangled slinky and this is the imprint.
No, this was off. I got it really good, but I got one.
Yeah.
Hey, one of you can write it. It's been a long time.
Yeah, I'll do that one.
I didn't even do anything.
So like when I asked, is anybody help seeing it?
Yeah, we actually let him type first.
No, this big black box.
If you do it that way, because I think
Well, I
that
don't
it's so
know, Bob,
close, I
unless
just
it's
can't find the.
Yeah, leave that one for me. Leave that one for me, Corey. I'll do that one.
There's one little move you have to do. I just can't.
Yeah.
I can't see it. Sorry about it.
No, don't be. I'm never sorry when I bother you.
Who's your honor?
And to be fair, he never is either. he does it way more than I do it to him. Okay, so let's talk about actually what we see here. What do those things all mean? What do they represent? All that kind of good. Where is the screen? All right. Okay, so explain, it's coming up, I promise. Explain emission spectrum and what it has to do with excitation and light energy. Okay, so here is, I'm going to do the one that was easier to distinguish, which was the one I did first? Mercury, right? Mercury. Okay. So Mercury's got its electron, so it's got an electron here, orbiting around it. But then it's got a couple other levels too, level 2 and level 3. Okay, so light comes in. Hits it, gets excited. Okay, that electron can do a couple of things. The first thing it can do is it can go up to the first level. Let's just jump and go all the way up to the second level. So it gets excited, goes all the way up to the second level. From there, it can do a couple of things. Let me make sure if I can try to get my colors as accurate as I can. What were the colors on that one again? It was like a green, yellow, and indigo, and was it an orange? Yeah. Okay. So what happens is it has three different things it can do. It can jump down one level. Let's say that makes orange. Okay, so that makes the orange color that you see. Or it can jump down 2 levels. And let's say that makes the green that you see. Or if it jumps down from the top to the middle, it can go from the middle to the bottom, and that makes that kind of violet that you saw. So each energy jump matches a light energy. Energy color. So, depending on what the atom is, you can figure out exactly what energy levels it has. So, what makes this unique or interesting or different is every atom is different. Every single one. Every single atom is different. So, not only do they all have different color bands, but you saw like on the neon it had lots of color bands. Mercury has fewer color bands. Hydrogen's just got a few. Carbon has a lot. Oxygen has a lot. Like, it depends. It just depends on the atom and what it's doing. And so every atom is a little bit different, and their colors are different, and how many there are different. And so everything is individual. And it's not like what we would think it would be, where there's just all these broad wave of energies. It can be all of these energies. No, it's really specific. It can be this energy, or this energy, or this energy, or this energy. It's not just anything and everything. It's only very particular, specific ones. Okay? So, how are energy and frequency related? I know what you're saying to yourself is, gosh, Mr. B, I really hope you've got an equation for me. And the answer is, I do. You're welcome. Okay? E equals H F. E is energy. It's measured in joules or electron volts. I'll explain the difference and when we use them here in a second. F is frequency. Okay, and the frequency is going to be in hertz. And then H is called Planck's constant. Never mind what that is for the moment, just it's Planck's constant. Good talk. So, what is Planck's constant? What does that have to do with this magical thing called quantization? Okay, so Planck's constant is a measure of the fundamental change in energy. Okay, so here's what you would think. First of all, light is a wave. It's a range of waves. You can have literally every single light wavelength all the way down from almost zero up to almost infinity. There's no limit in between. You can do every single wavelength in there. So, if energy is dependent on the frequency, so E equals HF, H is a number, F is a frequency. So if E depends on the frequency, you would think that if every single frequency of light is possible, then for every single energy is possible, and that is not true. The reason why it's not true is because you multiply F by H, and H is a specific number. And so it's kind of like, what if I gave you every single number, and I said, so F is every single number 1 through 100, okay? And F equals 2 times, F times 2 equals, yay! I don't know, I'm just making something up. But if I took 1 times 2 gives me 2. That means 1 is not an answer. 2 times 2 is 4. That means 2 is not an answer. When I multiply the frequency by H, I miss out some energies. What this means is, and the simplest way to explain Planck's constant, it means that a measure of fundamental change in energy means only certain specific, so they're called quanta, values exist. This is where quantum mechanics comes from. Okay? There's very specific values that can exist. They're called quanta. They're very strategic, bite-sized, this little bit packet of stuff. And they're based off of Planck's constant. Planck's constant has 2 values. I'm going to give them both to you. I will tell you the specific scenario of using each, so that you know exactly which one to use. I will never make it confusing about which one you should use. I'll like bold the units or whatever the case may be. Okay, so the one that is the real one is this. Planck's constant, H equals 6.63 times 10 to the negative 34th joule seconds. That is like the real actual value for Planck's constant. 10 to the negative 34th. Yes. 10 to the negative 34th joule seconds. Okay? This is basically the smallest realistic number that you can reach. Like, this is about, like, you can't, like, you can measure things smaller than that, right? But this number is, like, the limit as to, when we talk about quantization, it's the smallest breakdown you can get. So sometimes it's called Planck time. You can get a time based off this, right, joule seconds. Planck time is like the smallest increment of time that could exist. Okay? This is not the value we're going to use most often. This is the one that is like the real actual value. The one that we're going to use most often is this one. 4.14. It's the one we're going to use in the lab today. Times 10 to the negative 15 EVSs. EVs. It's electron volt seconds. And you're probably saying to yourself, Mr. B, why? And here's why. The reason we're using electron volt seconds is because that is what we use when we talk about particles of light. And where we use this today is with light. When you're talking about light, it's easier to use electron volts because light is very tiny and small. So therefore, we want to use a very tiny and small number. I know negative 15 is not tiny and small, but like it needs to be more realistic. Like negative 34, that's based off of like huge objects. That's really hard to deal with. Negative 15 electron volts seconds, that's a lot simpler to manage. Not easy, but simpler for us to manage. Okay? So that's kind of where we are with that. All right. Let's go ahead and let's jump to the lab. I do want to jump to the lab, but we only have 10 minutes. By the time we got set up, it would be time to be done. I'll make you a deal. We'll do 5 more minutes of notes, and then I'll do a 5-minute story time. Deal? Everyone's wide awake. Great. This is awesome. It's going great. I'm really enjoying this. Okay. What's the origin of quantum theory? So the origin of quantum theory and this idea of a quantum. I don't want to worry about it. Let's do this one. Explain the photoelectric effect. Okay? Photoelectric effect was something really weird and interesting that happened. And that's what you guys are going to do next class. You guys are going to do the experiment with this. Okay? Photoelectric effect was this phenomenon here. Okay. What they did is they shone light. Come on, work. There you are. They shone light on a surface, on a metal surface. In this case, it is a sodium surface. When they did that, little electrons bounced off of the surface and went. And if they put it in a circuit, they created a current in the circuit. This is how solar cells work. So solar power is how it works. Okay? And they were like, ooh, that's great. Let's do this, but most of the time we don't have these bright purple lights. So most of the time we have like regular-ish, like reddish lights or yellowish, orangish lights. And they did it, and nothing happened. And they're like, well, that doesn't make any sense. These are like regular lights. Why are they not working for regular lights? And they were like, oh, the lights aren't bright enough. So what they did is they turned the lights up to 11, and nothing happened. And they were like, well, that doesn't make any sense, because while it wasn't very noticeable, if I went for purple, if it was barely on, it still worked. So why is it that purple is working even when it's not very bright, but red isn't, yellow isn't, orange isn't, even when it is really bright? And that's what they were trying to figure out. Because the problem was it should work for every color as long as the light's bright enough. And it just didn't. It only worked for very, very, very specific frequencies of light. It didn't work for all of them. And the brightness only made it happen more often. It didn't make it happen better or worse or anything else like that. It just made it either worked or it didn't, and then the brightness determined how much it worked. So what was the photoelectric effect? So light shined on a metal surface and released electrons. And I'm just going to write in parentheses, solar power. So that's how solar power works. Okay, so explain the problem. The problem was, wave theory said, so the idea that light behaves like waves, which is what we've always been talking about, wave theory says any color of light should do this. If it is bright enough. But it doesn't. So what you guys are going to do next class with the lab is you guys are going to actually figure out how does